All right, welcome to the deep dive. Today we're going to dive into something called many-sorted logic. And I think when most people think about logic, they kind of think about like the if-then statements.
Right.
But usually when we're thinking about that kind of logic, it's like everything is in one big bucket, one big universe. And many-sorted logic, or MSL, it kind of changes that. It lets us work with different categories. Like we call these categories sorts of objects. Like
Yeah.
like in geometry, points and lines are different kinds of things.
Right.
So many sorted logic kind of gives us a formal way to keep track of these distinctions when we're reasoning. And this turns out to be really helpful in all sorts of areas like mathematics, philosophy, computer science, even in like formal semantics, which is the study of the meaning of language.
Yeah. What's so cool about this is that uh, it kind of just reflects the way we already think about the world anyway.
Mm.
Like we don't just see a big like jumble of stuff.
Right.
We categorize right like apples and oranges.
Yeah.
Or ideas and like physical objects.
Yeah.
Or different types of data.
Yeah.
So many sorted logic just gives us like a formal way to reflect that kind of categorization within a logic system.
Yeah.
And it lets us be a lot more precise with how we model, reality in our reasoning.
Yeah, exactly. And so in this deep dive, we're going to see just how powerful and how flexible this approach is, especially when we're trying to understand different logical systems and how they all relate to each other. And the cool thing is even though it gives us this extra ability to kind of keep track of these different sorts of things, MSL is still within the boundaries of first order logic. And
Yeah.
why that's important is because it means that it still has a lot of the desirable properties that we want logic to have, like completeness, right? The idea that if something is logically true, then we can also prove it.
Right.
So, and we'll talk about that in a lot more detail as we go.
Yeah, if you take a step back, I think it's worth mentioning some of the key figures who kind of started many-sorted logic. So Hao Wang, back in 1952, he kind of came up with a system for MSL. And then later, Solomon Pfefferman in the late 1960s, he really developed it further, came up with something called sequent calculus for MSL. And he also proved some important things called metatheorems. And these metatheorems are basically results about the logic itself.
Right.
Like completeness or interpolation. And these results tell us like what MSL can and can't do.
Right.
So their work really like established MSL as this important area of logic.
Absolutely. So to give you kind of a roadmap of where we're going today, we're going to start by looking at the kind of the nuts and bolts, the syntax and semantics of MSL. And we'll use some examples to kind of make it concrete. Then we'll explore the calculus, which is basically how we do proofs with an MSL. And then we'll talk about this really important idea of completeness, making sure our system actually works the way we want it to. And then finally, we're going to see how MSL kind of acts as this unifying framework that lets us translate and understand a bunch of other logical systems.
Yeah.
So to start with, let's unpack this idea of syntax and semantics.
Okay. So at its core, a many-sorted logic is defined by its sorts.
Yeah.
And as we were saying before, those are those distinct categories of things,
Right.
So then it also has like an alphabet, and that includes variables. But here's the important thing. In MSL, each sort that you have, you get variables specifically for things of that sort. So for example, if you had a sort for like people and a sort for places, you would have like variables that could only stand for people and variables that could only stand for places.
Yeah.
It's like you're keeping your logical building blocks in like separate containers, and each container is labeled.
Right.
Yeah. And we also have like relation symbols, function symbols, and constant symbols.
Right.
And the important thing here is that these symbols each have a rank, and the rank tells you what sorts of things that symbol can apply to.
Right.
And for functions and constants, the rank also tells you what sort of thing they give you as output. This makes sure that the statements we make sense with the categories that we've set up.
Yeah.
So like a function that adds two numbers, right, that wouldn't make sense to apply to like a color and a number.
Right.
The rank kind of enforces that.
Right. Yeah. And it's kind of like it has this built-in type system.
Yeah, exactly.
Yeah.
So to make this concrete, let's look at an example. So Euclid's first principle.
Okay.
So it says a straight line can be drawn joining any 2 points.
Right.
So we can actually formalize this pretty nicely into two-sorted logic.
Right.
So, where we have one sort for lines, let's call that L.
Right.
And one for points, we'll call that P.
Okay.
So we can use variables like 6 and $1 to represent lines because they're of the sort L,
Right.
and variable 7 and $1 to represent points because they're of sort P.
Okay.
And then we can introduce like a special predicate, a three-place predicate called join, that takes a line and 2 points as input, and it tells us whether that line joins those 2 points.
Okay.
So the rank of join would be LPP because it takes one line and 2 points.
Got it. Yeah.
So join XY would mean line 6Y joins the point 6 and $1.
Okay.
Yeah.
So in symbolic form, Euclid's principle would be something like, for all points 6 in I of sort P, if 6 of all is not equal to dal,
Right.
then there exists a line 6 of Y of sort such that join 6Y holds. And then furthermore, for any other line also of sort L, if join XY also holds, then $6 must be the same line.
Right. Yeah. So you can see how those sorts kind of guide how we use the predicate join. It makes sense to talk about a line joining 2 points. But in this system, it wouldn't even be grammatically correct to talk about a point joining 2 lines.
Right. Yeah. Yeah. It's kind of like the grammar is built in.
Exactly.
Yeah.
It's like this built-in type checking. And that's really at the heart of many sorted logic.
Yeah. Yeah.
So we've got the symbols. Now we need to talk about the formal language that we build with these symbols. So we have terms and formulas.
Okay.
In MSL, every term, which is, basically an expression that refers to an object, has a specific sort.
Right.
So variables and constants of a certain sort, they're terms of that sort.
Yeah.
And if you have a function symbol that takes certain sorts as input and gives you a different sort as output, well, if you apply that function to terms of the right input sorts, then you get a new term that has the output sort. So again, those sorts are always maintained.
Okay, yeah. So then the formulas are the statements that we make about these terms.
Right, exactly.
So the simplest kind of formulas, we call those atomic formulas. And you get those by applying like a relation symbol to terms of the right sorts,
Yeah.
and the ranks will tell you what sorts are the right sorts.
Right.
So, and then we also usually have like an equality symbol that we can use to compare terms.
Right.
But often in a many-sorted setting, that equality is also sort-specific, meaning you can only compare things that are of the same sort.
Right.
So then we can build more complicated formulas using the usual logical stuff, like and, or, not.
Right.
And then, most importantly, we have quantifiers, like for all, and there exists.
Yeah.
But those are sort-specific too.
Right.
So you can say, like, for all points, $6, meaning you're only talking about things that are of the sort point.
Yeah.
Or there exists a line, dollars, meaning you're only talking about line.
Exactly.
Right.
So we've got the language. Now, how do we give meaning to these formulas?
Mm-hmm.
So that's where semantics comes in. And in MSL, we talk about many-sorted structures.
Okay.
So a many-sorted structure has a bunch of different non-empty sets. And for each sort in our language, we have one of those sets, and we call that its domain.
Okay.
So if your logic has sorts for like numbers and colors, your structure will have a domain for numbers and a domain for colors.
Okay.
And those domains are going to be non-empty.
Right.
And then your relation symbols get interpreted as, actual relationships between elements of those domains.
Right.
And your function symbols get interpreted as actual functions that map between those domains.
Right.
But it all has to be in accordance with the rank that you've given those symbols.
Right.
So the interpretations always respect the sort of distinctions that we've made.
Got it. So you mentioned strict versus liberal relations earlier.
Oh, right.
Could you maybe clarify what the difference is?
Yeah, sure. So a strict relation, like the one we saw with the join example, it has its rank fully specified. So it tells you exactly what sorts are allowed for each of its arguments. So join line, point, that's a strict relation.
Okay.
A liberal relation, on the other hand, it only has its overall number of arguments specified, but it can relate objects from any of the domains in our structure.
Okay.
And while liberal relations can be useful, I think the real strength of MSL comes from using strict relations, because those strict relations really let us model the relationships between different categories in a much more controlled way.
Right, right. It's all about kind of keeping those boundaries between the categories clear.
Yeah, exactly.
So I think you had a really interesting example that kind of brought this all together. You mentioned something about the Book of Perfect Emptiness.
Yeah, that's right.
So how does many-sorted logic allow us to kind of like formalize something from philosophy?
Yeah, so this example, it comes from this ancient Taoist text, the Lizi.
Okay.
And it presents an argument about existence in time. And so to analyze it logically, we can use a two-sorted language.
Okay.
So one sort for objects, like things that can exist,
Okay.
and one sort for instance of time.
Okay.
And then we can have predicates like exists at that takes an object and a time as input.
Okay.
And it tells us whether that object exists at that time.
Got it.
And we could also have predicates like precedes
Okay.
that takes two times as input and tells us whether one time comes before the other.
Okay.
And maybe constants like now and beginning.
Yeah.
Both of those would be of the sort time.
Right, right. So I'm starting to see that kind of like the philosophical angle here. It's like we're not just talking about some like abstract thing existing or not existing. We're saying like, when does it exist?
Exactly.
Does it exist now?
Right.
Or, how has its existence changed over time?
Yeah. And so the argument in the Book of Perfect Emptiness, it basically says, if things exist now and the beginning of time precedes now, then things must have existed at the beginning of time.
Okay.
And, this argument might rely on an assumption, like if an object exists at a time and there was an earlier time, then that object must have also existed at that earlier time. Or maybe the argument is trying to question that assumption.
Right, right.
But using our two-sorted logic, we can actually express those premises really precisely.
Yeah, yeah.
Like something exists now becomes, there's an object $6 such that exists now.
Okay.
And the conclusion, something existed at the beginning of time, would be there exists an object here such that exists acting.
Right, right.
And that hidden assumption about existence at earlier times would involve quantifying over both objects and instance of time and connecting them with that precedes predicate.
Got it.
So by formalizing these philosophical ideas in MSL, we can really see the logical structure of the argument.
Yeah.
And we can analyze it much more rigorously than if we just use ordinary language.
Absolutely. So many-sorted logic is like this really great tool for philosophical inquiry.
Yeah.
Because it lets you take these abstract concepts and put them into a precise language.
Exactly. It makes the logic much clearer.
Yeah, yeah. Okay, so we've talked about the language of many-sorted logic. We've talked about these structures that we use to give it meaning. So how do we actually figure out if a statement is true or false in this system? Like, I think that's where the semantics comes in.
Right, yeah.
And specifically how Tarski's truth definition gets adapted for many-sorted logic.
Yeah. So the main idea is the same as in classical logic. Truth in a many-sorted structure is defined recursively. So what that means is, like, the truth of a big, complicated formula depends on the truth of its smaller parts.
Right.
So for an atomic formula, like join $6, X, Y, dollars, whether or not that's true depends on whether the actual objects in our structure that those variables, refer to, whether those objects actually have that joining relationship. And for more complex formulas, the ones that we make with and or and not, and those quantifiers, the truth conditions are exactly the same as you would expect. The main change in MSL is that when we're assigning values to our variables, we have to make sure that those values come from the right domains.
Right.
So a variable that's supposed to stand for a point can't be assigned a value that's actually a line.
Right, right. That sort of like type checking extends to the quantifiers as well.
Yeah.
So when you're saying like, for all $6 of sort point,
yeah.
you're only looking at the actual points in the structure.
Exactly. And with this definition of truth, we can then talk about things like, satisfiability, validity, and logical consequence.
Okay.
So satisfiability means, whether there's some structure and some way of assigning values to the variables that make the formula true.
Okay.
Validity means whether the formula is true in every structure.
Okay.
And logical consequence, means whether one formula logically follows from a set of other formulas.
Right.
And all of these core ideas from logic, they carry over to the many-sorted setting really nicely.
Got it. Okay, so we've talked about the language and how to give it meaning. Now let's talk about how we actually prove things in many-sorted logic. Like, how do we actually do those proofs?
Yeah. So thankfully, the systems we use for ordinary first-order logic, we can adapt those to MSL pretty naturally.
Okay.
Because a lot of the basic rules for how we deal with, like, and or implies, those stay pretty much the same.
Okay.
But we have to be careful with the rules for quantifiers and substitution, because we always have to keep track of the sorts.
Right, yeah. So it's kind of like you're taking the existing logic tools and you're just adding like a sort of awareness layer to each tool.
Yeah, yeah, exactly.
Okay.
And just like in any logical system, we care a lot about soundness and completeness.
Right.
So soundness means our proof system only lets us prove things that are actually logically true.
Right.
And completeness means that our proof system is strong enough to prove all the things that are logically true.
Right.
And thankfully, many sorted logic does have completeness.
Okay.
So we can take this really well-established proof called the Henkin-style completeness proof, and we can adapt that to the many-sorted setting.
Okay.
And basically what this proof shows is that if you have a set of formulas that doesn't lead to a contradiction, meaning they're consistent,
Okay.
then there must be some structure where all those formulas are true.
Right.
So that means our proof system can capture all the truths of our system.
So that's a pretty big deal. It's like it's saying that the way we're proving things
Right.
really matches up with the way the structures actually work.
Yeah, exactly. And we also get other important results from this completeness theorem.
Okay.
We get weak completeness, which means that all the formulas that are true in every structure are also provable. We get the compactness theorem, which is super useful. It basically says that if every finite part of a set of formulas has a model, then the whole set also has a model.
Okay.
And then we get the Lowenheim-Skolin theorem, which tells us that if a set of formulas has a model,
Right.
then it also has a model that's not too big.
Okay.
So all of these results give us like a really deep understanding of how MSL works.
Right. So even though we have these different sorts, many sorted logic still has all those nice properties.
Yeah.
It's still really well behaved.
It is. And so it makes you wonder, is many sorted logic like more powerful than ordinary first order logic?
Right.
Can you do more with it?
Yeah.
Can you prove more things?
Yeah. Does it let you express things that you can't express otherwise?
Yeah. So actually, according to some results, like Lindstrom's theorem, the answer is no.
Okay.
So Lindstrom's theorem says that first-order logic is kind of like the most powerful logic that still has both compactness and the Lowenheim-Skolin property. And since MSL also has those properties, it means that it's not like fundamentally stronger than first-order logic.
Okay.
It's more like a more convenient way of working within first-order logic.
Yeah.
It's like having a better organized tool docs,
Right.
but all the tools are still like fundamentally the same.
Right. You're just keeping them in separate compartments.
Yeah, exactly.
That makes sense. Okay, so now let's get into how MSL can be used to understand other logics. You know, you mentioned this idea of it being like a unifying framework.
Yeah.
So how does that work?
Yeah, so the idea is that you can often take other logics, like, maybe they deal with necessity or time, and you can translate them into many sorted logic.
Okay.
And then by doing that, you can learn a lot about those other logics.
Okay.
Like you might be able to use all the tools and techniques that we have for MSL
Right.
to study those other logics. And you might even be able to take some of those nice properties that MSL has, like completeness, and show that those other logics have them too.
Right. So it's like you're finding this common language for all these different ways of reasoning.
Yeah, exactly.
Okay.
So there are a bunch of different ways to do these translations. Some focus on preserving proofs. If you can prove something in one logic, you should be able to prove something equivalent in the translated logic.
Okay.
Others are more about how the structures of the different logics are related.
Right.
And what we're mostly going to focus on here is model theoretical translation,
Okay.
where we're taking another logic and translating it into many sorted logic.
Okay. And I think you had an example with modal logic.
Yeah, that's right.
So for people who maybe aren't familiar, what is modal logic?
Yeah, so modal logic is this extension of classical logic where you have these special operators that let you talk about necessity and possibility.
Okay.
So like you have this box operator.
Okay.
And that usually means it's necessary that. So like box P would mean it's necessary that P is true.
Okay.
And then you have the diamond operator.
Okay.
And that usually means it's possible that.
Okay.
So a diamond P would mean it's possible that P is true.
Okay.
And the way we usually give meaning to these operators is through things called Kripke structures.
Oh.
And a Kripke structure has a set of possible worlds. And it has this relationship between those worlds called an accessibility relation.
Right.
So you can think of these worlds as like different scenarios or possibilities.
Yeah.
And the accessibility relation tells you which scenarios you can like reach from another scenario.
Okay, yeah. So box P is true in a world if P is true in all the worlds that you can access from that world.
Exactly, yeah.
And diamond P is true if P is true in at least one of those worlds.
Exactly.
Okay.
So how do we translate this into many-sorted logic? Well, we can basically create this first-order language that talks about crypt key structures. So we can have a sort for the possible worlds, and we can call that sort world.
Okay.
And then we can have this binary relation symbol,
Okay.
like R, that represents the accessibility relation between worlds.
Okay.
So R dollar would mean that world dollars is accessible from world dollars.
Okay.
And then for each atomic proposition in our modal logic, like, P or Q, we can introduce a predicate in our first-order language.
Hmm.
So like P would mean that the proposition P is true in world dollars.
Got it.
And then the modal operators, those get translated into quantifiers over worlds.
Okay.
So for example, box, which means it's necessary that is true,
Right.
that gets translated into for all worlds dollars. If other dollars is accessible from dollar, then the translation of phi is true at dollars.
Okay.
And similarly, diamond, which means it's possible that head's true,
Right.
that gets translated into there exists a world dollars such that dollars is accessible from dollars, and the translation of phi is true at dollars.
Okay. Okay. So this translation basically shows how the modal operators and the quantifiers over worlds, they kind of correspond to each other.
Yeah, exactly. There's this result called the switch lemma that basically says that a modal formula is true in a world in a Kripke structure, if and only if its translation is true in the corresponding many-sorted structure.
Got it. Okay.
Yeah.
So we're really connecting these two different systems in a pretty deep way.
Yeah. And one of the really cool things about this translation is that basic modal logic can actually be translated into this fragment of first-order logic called the two-variable fragment.
Okay.
And in this fragment, you only need two different variable symbols to write down any formula.
Okay.
And it turns out that figuring out whether a formula in this fragment is satisfiable,
Right.
whether it can be true in some structure,
Right.
that problem is decidable.
Okay.
Meaning there's an algorithm that can always give you an answer.
Right.
And because our translation from modal logic preserves satisfiability, it means that basic modal logic is decidable too.
Okay. So we're using this translation to figure out something important about modal logic itself.
Yeah, exactly.
We're using MSL to prove that modal logic is decidable.
Yeah.
That's cool.
So when we're trying to prove completeness for some logic by translating it into many-sorted logic, there's a kind of three-step process.
Okay.
And this process kind of shows us that our logic is well-behaved.
Okay. Okay. So walk me through those steps. What are the three steps?
All right, so the first step is what we call level 1.
Okay.
And the goal here is to establish what's called a representation theorem.
Okay.
So what you do is you define a translation from your logic, let's call it XL, into a many-sorted language, MSL sup XL sup.
Okay.
You also define a way to convert structures from XL into structures for MSL sup XL sup.
Okay.
And what you're trying to show is that a formula is valid in XL, meaning it's true in every XL structure,
Right.
if and only if its translation is a logical consequence of some set of sentences in MSL sup XL sup.
Okay.
And we usually call that set of sentences and. So basically captures the key properties of the XL structures.
Got it.
And if you can do this, if you can establish this representation theorem, it often means that your original logic, XL, is what we call abstractly complete, meaning you can list out all the valid formulas of XL.
Yeah. Okay. So level 1 is basically showing that the idea of truth in your original logic can be expressed in many sorted logic using this special set of axioms.
Exactly.
Okay.
So then we move on to level 2.
Okay.
And here, if your original logic has this idea of logical consequence, not just validity,
Right.
then you want to prove what's called a main theorem.
Okay.
And this theorem says that a formula is a logical consequence of a set of formulas in XL.
Right.
If and only if the translation of it is a logical consequence of the translations of the formulas in I, along with that set of axioms are,
Yeah.
but all in MSL sup XL sup.
Okay.
So for this, you usually need to be able to convert structures from XL to MSL sup XL sup, but you also need to go the other way around. You need to be able to take structures that satisfy in MSL sup XL sup and convert those back into XL structures.
Okay.
And the cool thing about this is that if your MSL subsec Excellus has properties like compactness or the Lowenheim-Skolem theorem,
Right.
then you can often show that your original logic XL has them too.
Okay. So level 2 is going beyond just like, looking at whether a formula is true in every structure.
Right.
It's looking at whether a formula follows from other formulas.
Right.
And it can help us figure out if our original logic has some of those nice properties that MSL has.
Exactly.
Okay.
And then finally, we have level 3.
Okay.
And this is where if your logic XL has a deductive calculus, a system for proving things,